So if I have 24.5 liters of oxygen, then I'm going to need twice as much hydrogen. So that's going to be 49 liters, 49.0 liters of hydrogen. All right, and so that would be a box like this, and a mole of gas is going to contain, do you know how many O2 molecules are in here? Well, mole is how many? Yeah, 6.022 times 10 to the 23rd. We call that number Avogadro's number. And so 6.022 times 10 to the 23rd oxygen molecules occupies 24.5 liters. And so if I double that and get 2 moles of gas, I'm going to need twice the volume. So we'll have 24.5 and then another 24.5 liters. So altogether 49 liters of hydrogen. All right, I'm going to have the same number of molecules, but the weight is going to be different. You know, so for example, if I just look at one box here, they're going to weigh different amounts because oxygen is a much heavier molecule. But interestingly, it's the same number of molecules in that particular volume. And the same thing, water weighs a different amount, but if I have 2 moles of gaseous water, it's going to occupy a volume of 49.0 liters. Now, if this is H2O liquid, then that's a different story. Because H2O liquid is not a gas anymore, and so gas is mostly empty space. You need this space for the molecules to move about. But for H2O liquid, what's going to happen is liquids aren't going to be full of empty space. So H2O liquid is going to occupy a much smaller volume. So if we blow it up like this, H2O liquid, well, 2 moles of H2O liquid is going to weigh 36 grams. Well, 36 grams means this is just going to be 36 milliliters of water. Just do 36 grams. And so rather than having 49 liters, we're going to put that 2 moles of liquid water in 36 milliliters. So this only works if we're dealing with gases. So for example, we couldn't say we're going to form 49 liters of water. That would be much more than 2 moles of water. And so the same goes for solids as well. You know, those solids can occupy even less space than that. They're more dense. And so this is essentially Avogadro's law here. You know, it doesn't, you know, the one thing about Avogadro's law is it doesn't have to be a mole. You know, we could have half a mole, you know, half a mole of O2 or a mole of H2. That's what we use stoichiometry for, because we don't always use 1 mole quantity. The same thing, we aren't always going to use 24.5 liters. We might use more or less. And so this is just, it's easy. We could just do, for every 1 liter of oxygen, we'll need 2 liters of hydrogen, and that's going to form 2 liters of H2O gas. So it's a 1 liter to 2 liter to 2 liter, or gallons, or cubic inches, whatever volume unit you want to use, because what happens is if we, let's say we start off with 3 gaseous particles, if we double it, we're going to get 6 gaseous particles, the volume doubles. If we triple it, you know, like here, we get 9 gaseous particles, the volume triples. So, like this is Avogadro's law. So if we incorporate Avogadro's law into the previous things that we were dealing with, we get something called the ideal gas law. That is, we take Charles, Boyle's, and Avogadro's law, combine them together. You don't have to know how they're combined, but you just have to know how to use this. This is the ideal gas law right here. PV equals nRT. So let's just focus on that. PV equals nRT. This just describes the physical characteristics of the gas. In other words, physical properties of things like pressure, volume, N is the number of moles, R is called the gas constant. Which we're going to memorize. 0.08206 liters times atmosphere divided by mole. Actually, you don't have to memorize it. We'll give it to you. That's a gas constant. And so the typical question is, do we have to measure everything? What do you want to know about a gas physically? Okay, these are the things we want to know about a gas physically. So let's have a gas here. We'd like to know the pressure. We'd like to know the volume. We'd like to know the amount and the temperature. And so if we know any of the three, so know that is measure 3, then calculate the 4th. And so we pick any of these 3, let's say, and then we can solve for the 4th. And so an example of that would be the volume. Let's solve for the volume. If we solve for the volume is going to equal nRT divided by P. According to this, people remember this as the Pepner equation. So if we look at this and rearrange it, we can solve for the volume. Now, the typical, let's see, let's call it 1.0. Actually, let's go with 1.0. Let's go 4 sig figs. 1.00 moles, 000 moles of gas. Temperature, we're going to do 298.15 Kelvin. And the pressure, we're going to do at 1,000 atmospheres. Okay, and so we just plug in the numbers here. And so this is just going to be 1,000 moles. And then R is 0.0. R is 0.08206. That's given, liters times atmosphere divided by mole, Kelvin. And then the temperature, 298.15 Kelvin, which is, that's what we call room temperature, divided by the pressure of 1.000 atmospheres. If we look at the units, the moles cancel, the Kelvin cancels, the atmospheres cancel, that just leaves us with liters. And so what is the volume of 1 mole of gas at room temperature and room pressure? So let's go ahead and calculate that. It's going to be 0.08206 times 298.15 is 24.46 sub 6 liters. And so, in other words, 1 mole of gas at room temperature and room pressure occupies a volume of 24.466 liters. In other words, to 3 sig figs, this would be 24.5 liters. And so this is where I got this number from, 24.5 liters for 1 mole of gas. That's how much space it occupies. And so this is a standard type of problem where we can do this kind of thing. We also can derive one more equation from this. We can derive a little bit more advanced version of the combined gas law. That is PV over NT is equal to R, which is a constant. So this ratio doesn't change. ratio is a constant. Therefore, what we can do is we can do P initial, V initial over N initial, T initial is equal to P final, V final over N final, T final. And so this is like just the same thing as the combined gas law, except it just has moles. So if you add some gas or remove gas, then we can use this. And so this is the combined gas law, where we can let some gas out of the container or add some gas into the container. In other words, we can change the number of moles.
So which one is it? The first one? Are they the same thing?
Well,
Or is the top one the combined gas law?
no, this is the combined gas law here. This is from the earlier chapter. The earlier chapter, the combined gas law that you had looked like this. And so it's just an additional thing of the moles. The moles can change. This is a previous chapter. If the number of moles doesn't change, then they cancel. And so let's take a look at this active exercise here. A 0.1000 mole sample of helium is placed in a piston and heated to 25.00 degrees C. The volume is adjusted to 4.600 liters, and the resulting pressure is measured at 0.5319 atmospheres. Use these data to determine the value of the universal gas constant. And so what they want us to do is they want to plug in P, V, N, and T, and then solve for R. And so we get to solve for any of the variables given 3 of the 4. And so here they're just saying, okay, we'll just rearrange this equation in terms of R. Here, R is equal to PV over NT. Then just plug in the pressure, the volume, the moles, and the temperature. The tricky thing is to make sure all the units cancel. If the units don't cancel, we have to do some unit conversions. Well, in this case, none of the units cancel. None of the units cancel. And we end up with an R of 0.08206 liters atmosphere per mole Kelvin. Now, this is a number that's usually given. This is just a 4 sig figs. So that's a number that's normally given or memorized. So that's just a calculation, just to verify for me. All right, so that example and my example, earlier example, are just examples of determination of a single variable. Now, determination of a single variable is just, okay, we have one of these unknowns. We have to be given the other 3. However, there are some special applications of the ideal gas law. Let's look at special applications. So this is single variable determination. This is an advanced combined gas law, or the more comprehensive combined gas law. And then we have some specialty applications. We'll look at the specialty applications. One is the molar mass of a gas. I don't use that equation there. I'm going to use it like this. Molar, okay, so we'll do one. Molar mass of a gas. Okay, the molar mass of a gas is, if I have a mole, how much does a mole of that gas weigh? And so in other words, it's equal to the mass of the gas divided by the number of moles. And so what we end up with is units would be grams per mole. grams per mole. Now the mass of the gas, this is given. The moles we can calculate using PV equals nRT. And so what we end up with is this. We're going to get the mass of the gas divided by, okay, solve this equation for N. Well, N is equal to PV over RT, like that. And so what we end up with is this. We end up with the mass times RT over PV. And so, what can we do? Okay, so this is one of the equations, molar mass of the gas. And so what we can do is we can measure the temperature, the pressure, and the volume. If we measure the temperature, pressure, and the volume of the gas, then we can solve for the molar mass. Okay, so I'm going to call it MM. So the molar mass is equal to the mass times RT over PV. Or, there's one other thing. Or, we know that the mass over volume, you know what mass over volume is called? The density. This is called the density. And I'll give it the symbol D. I think that's what our book uses. Just make sure. Yeah, D. And so we can use this alternate equation, or it's equal to the density times RT over PV. So if we know the density of the gas, then we can calculate the molar mass of that gas as well. Oops, sorry, no P, RT over P. All right, that's one. Likewise, we can calculate the density of the gas, too. Normally, if we want the density, we do some experiment. But for the density of the gas, we can determine that the density is equal to the mass over volume. So the mass is going to be given. The volume we can calculate using PV equals nRT. And so this is going to be the mass divided by, okay, solve this for V. We solve this for V, it's nRT over P. So this is going to equal the mass times the pressure divided by nRT. However, we know something, the mass over volume, is density, but the mass over moles, do you know what that is? It's grams per mole. Mass over moles is also called the molar mass. So the mass divided by moles is the molar mass. And so what we could do is we could say that the density is equal to the molar mass times P divided by RT. And so we could calculate the density of any gas at any pressure and temperature, can calculate density of any gas at any temperature and pressure. So maybe let's do an example of the density calculation here. let's calculate the density of hydrogen. At 298 Kelvin in 1 atmosphere. And the density of nitrogen at 298 Kelvin in 1 atmosphere. Okay, can you go ahead and do those two